welcome to AI Peer Review. So there's this really interesting, almost fundamental challenge right now in the AI landscape. We have all these powerful vision language models, VLMs, right? And many are open weight, which is great. But here's the catch. A lot of them are still learning from data that's basically been distilled from proprietary closed source models.
Right. Distill. It's like trying to bake a cake just by tasting someone else's slice. You don't get the actual recipe.
Exactly.
Yeah.
So what if we could bake that cake from scratch?
Yeah.
You know, truly open ingredients, totally transparent process.
Uh-huh.
Well, that's what a new CVPR 2025 paper is really digging into. It's called Molmo and PixMo, Open Weights and Open Data for State-of-the-Art Vision Language Models. It's coming out of the Allen Institute for AI in the University of Washington. And for those of you who follow AI vision, you'll definitely recognize one of the co-authors, Ross Gershik. I mean, truly, one of the jotes of the AI vision field. Huge name.
Oh, absolutely. And this paper, it's addressing a really critical gap that many of us in the AI community have been, grappling with. For a while now, the open source community has been fantastic at reproducing and adapting VLM capabilities, really good at that. But we've kind of lacked that foundational knowledge on building genuinely high-performing VLMs right from the ground up without leaning on those proprietary systems. So this work isn't just, hey, here's another model. It's really about pushing the boundaries of openness in AI, fostering truly independent innovation.
Right. So our mission today is to unpack this. Look at the key contributions from their novel data collection approach to some smart architectural stuff. We really want to understand why Molmo feels like such a significant step forward for the whole open source community.
Oh.
Okay, let's dive into what makes Molmo tick. First, let's just clarify this whole openness imperative thing.
Yeah.
Because right now, the VLM scene, it's still pretty dominated by proprietary giants, right? GPT-4o, Gemini 1.5 Pro, Claude 3.5 Sonnet.
Yeah, the big players.
And we have these great open weight models, but there's this subtle detail. Their training data. Often, it traces back to those closed systems. You mentioned LOVA earlier. They might use something like Share GPT-4v, which actually uses GPT-4v to generate image captions.
Right. So it's learning from the output of the closed model, not the original processor data.
Exactly. It's like we're building open models, but they're basically reflections, distillations. We're reverse engineering behavior, which fundamentally limits our true understanding and, independent innovation.
And this distillation approach, it really has profound implications for actual scientific exploration. If our best open models are just sort of derived from closed ones, the community misses out on that crucial foundational knowledge. We don't fully get how to build these things from scratch, and that really constrains our ability to innovate independently. It begs the question, can open source truly break new ground, or are we just constantly playing catch-up, relying on proprietary systems to set the direction?
That's exactly where Molmo comes in, positioning itself as a real game changer. The paper really emphasizes this commitment to being state-of-the-art in its class of openness, and that's not just talk. It means Molmo offers fully open model weights, fully open training data, and fully open source code. Crucially, without any reliance on synthetic data generated by other VLMs. That feels like a true paradigm shift, moving towards more transparency, more collaborative AI development.
Indeed. And the authors are quite clear, Molmo's success isn't just luck. It comes down to careful modeling choices, a really well-tuned training pipeline, and maybe most critically, the quality and the innovative collection methods for their new data sets. Which brings us perfectly to the heart of this breakthrough, the data itself, which they've called PixMo.
Ah, PixMo. Yeah, this is the absolute cornerstone, isn't it? And this is where it gets really compelling because, like you said, they're explicit. All PixMo datasets were collected without using external VLMs. That's core to their from-scratch idea. Let's start with PixMo Cap. That's their pre-training dataset. We're talking 712,000 diverse images paired with what they call highly detailed dense captions.
And highly detailed is almost an understatement here.
Right. The average caption length is, get this, 196 words. Compare that to Coco, maybe 11 words. Or localized narratives, around 37. It's a massive leap in detail.
Huge difference, really rich data.
And here's the really clever part for PixMo Cap, how they got that detail. The modality switching trick. Instead of asking human annotators to sit there and type these super long detailed descriptions, they asked them to just speak them for 60 to 90 seconds.
Ah, smart.
Yeah. Turns out people are way more comprehensive, more nuanced when they talk. And it's faster. Plus, they even captured an audio receipt for each description as proof no VLM was involved. This modality switching, it sounds like a genuinely innovative hack for data collection, doesn't it?
It really is. It's an excellent solution to a known bottleneck in annotation, and it directly tackles the quality issue you see in some other big data sets. And what's fascinating is, even after collecting all this rich human description, then they used a language-only LLM, but not to generate the captions from scratch.
Yeah.
No, it was specifically to summarize and enhance the raw human transcripts.
Okay, so refining, not generating.
Exactly. It's a smart, targeted blend. Human effort provides the core nuance, the observation, and then there's just a bit of LLM assistance for cleaning it up. It really underlines that even advanced LLMs struggle to replicate that kind of deep context you get from a human just looking and describing.
Okay, moving on then. There's PixMo points. This one sounds incredibly innovative. A 2D pointing data set. And this is where it gets really interesting for like practical applications
Yeah, this has huge potential.
because it tackles three things. One, letting the model point to stuff you describe in an image. Two, letting it count by pointing at each thing. And three, using pointing as a way to visually explain its answer.
Mm-hmm.
So, they show this cafeteria scene in the paper. You could ask it to count the tables. And it would actually point to each one before saying, okay, 15 tables.
Which is a little grounding.
Right.
Yeah.
Or there's a desk with stationery. Ask, what can I write with? And it highlights the pens and pencils. Or on a motorcycle dashboard image, where's the odometer? Bang, it points right to it. Even in that Seattle skyline picture, you ask it to point to Mount Rainier, and it does.
And the technical advantage here with PixMo points is pretty significant. Collecting pointing data is just way faster, much less labor-intensive than drawing bounding boxes or full segmentation masks,
Right, less work for annotation.
which let them gather over 2.3 million grounding annotations. That's a huge number. And if you think bigger picture, this is incredibly valuable. Imagine future robotics, right? Or maybe smarter augmented reality glasses. An AI that doesn't just understand find the remote, but can actually point to it on your messy coffee table.
Yeah, that would be useful.
It really opens up this important future direction where VLMs help agents, robots, web agents, accessibility tools, whatever, to actually act by pointing in their environment, pointing to a navigation spot, an object to grab, a button on a screen. Very powerful concept.
And the data doesn't stop there. They also have PixMo Ask Model Anything. That's for free-form Q&A. And again, humans were in the loop, interactively editing responses from a language-only LLM to ensure quality.
Quality control is key.
Then you've got the novel synthetic datasets, PixMo Docs, PixMo Clocks, PixMo Cat QA, PixMo Count, and the crucial bit, sticking to their philosophy.
Well.
Even these were generated without using VLMs.
Right, maintaining that independence.
So for PixMo Docs, they actually generated code for things like charts and tables. They show a U.S. music sales chart, a market analysis table, and the figures. Then they created Q&A pairs directly from that code.
Interesting approach, grounded in the structure.
And similarly for PixMo clocks, they rendered synthetic clocks, like that cool vintage watch face showing 8.26.1, and then made Q&A from those exact renderings.
So what's particularly innovative about this synthetic data approach?
Well, I think it's the sheer volume, sure, but more importantly, the method. This commitment to human-sourced data and non-VLM synthetic data is what really sets Molmo apart.
Yeah, it proves you can build comprehensive, high-quality multimodal datasets without relying on the very proprietary systems you're trying to offer an open alternative to. And this careful VLM-free generation for the synthetic parts means they have complete control over the ground truth. They avoid inheriting weird biases or limitations from existing black box models. It's clean.
So with all this amazing data, you're probably wondering how Molmo actually uses it and how it performs so well. Let's peek under the hood a bit at the architecture and some of the training insights. What are the nuts and bolts here?
Well, architecturally, Molmo uses a pretty standard VLM setup at its core. You've got a vision transformer, a VIT to process the images,
Right, the vision encoder.
a large language model for the text side, and then a connector module that bridges the vision and language parts. But while the base is standard, they've layered in some really clever improvements.
Okay, well, like,
One key thing is their multi-crop strategy, but specifically with overlapping crops.
multi-crop. So dealing with image resolution issues.
Exactly. Standard VITs can struggle with fine-grained stuff, like reading text in an image or getting tiny details if they only see the image at one fixed, often low resolution. So Molmo's solution is to tile the image with multiple higher resolution square crops, plus they keep a low-res overview of the whole image. Each crop gets processed.
Okay, but what's the deal with the overlapping part?
Right, so they address a known issue with simple tiling. Patches near the border of a crop can lack context from what's just outside that crop. By letting the crops overlap, they show this nicely in Figure 3. With that bike image, they ensure that the central patches within each crop get encoded with richer context from their neighbors.
I see. So information doesn't get lost at the seams.
Precisely.
Hmm.
And interestingly, the features from the overlapping regions themselves aren't directly passed to the LLM, but just having processed the image this way significantly improves the results. It's a smart architectural refinement.
Okay, clever. What else? Training.
They also refined the training with a simplified two-stage pipeline. A lot of previous work had this extra separate stage just for tuning the vision language connector part, often using kind of noisy web scale data.
Right, I've seen that.
Molmo just skips that whole separate stage. Instead, right at the start of the main training, they apply a higher learning rate and a shorter warm-up period just to the connector parameters.
So the connector learns faster initially.
Yeah, it allows those parameters to adjust more quickly and efficiently alongside everything else.
And the benefit there.
Well, it clearly reduces training time and complexity. You just have fewer stages to manage. And importantly, it eliminates the need for that often noisy, sometimes problematic web scale data that was typically used just for that connector tuning phase. So it's more elegant, more efficient, and boosts performance.
Nice. Any other interesting details under the hood?
Yeah, a few other things contribute. They made some vision language connector improvements. They found that taking features from specific VIT layers, the third to last and 10th from last apparently, and then using multi-headed attention pooling to combine them, worked better than just simple concatenation.
Attention pooling. So letting the model intelligently weigh and select the most relevant visual bits.
Pretty much, yeah. Instead of just mashing everything together, they also used text-only dropout during pre-training.
Text-only dropout. How does that help?
It seems subtle, but it's quite impactful. By sometimes masking out the text input, it forces the model to rely more heavily on the image itself to generate the caption or answer. It discourages just relying on language patterns and biases, which seems to improve downstream task performance.
Makes sense. Encourage visual grounding.
And one last efficiency thing: efficient handling of multi-annotated images. Often you have multiple captions or Q&A pairs for the same image, instead of feeding the image through the encoder separately for each text annotation.
Which would be redundant.
Totally redundant. They package all the text annotations for one image into a single long sequence, using masked attention so each piece of text only attends to the image in itself. This cut down the number of images they actually needed to process by 2/3, effectively slashing training time by more than half. A really smart engineering solution for training at scale.
Wow, okay. So lots of careful work on the data, some clever architectural tweaks, and smart training efficiencies. Which brings us to the big question. How does Molmo actually stack up? Does all this work pay off in performance? The paper dives into evaluation, using both academic benchmarks and, interestingly, a lot of human evaluation.
Yeah, and the results are pretty compelling.
So what's the headline number?
The headline is that Molmo 72B, which is their best and largest model, doesn't just get the highest score among open models on a combined academic benchmark. It also ranks second overall based on human preference evaluations, just behind GPT-4o.
Second only to GPT-4o in human preference. For a fully open model built from scratch, that's huge.
It's absolutely a monumental win for the open source community. It's proof positive that you don't need to rely on distillation or proprietary data to achieve truly state-of-the-art results.
Right. It shifts the dynamic, enables that independent innovation we talked about.
Exactly. It democratizes access to these cutting-edge VLM capabilities for anyone to build on. And this model, Molmo 72B, it actually outperforms several other top-tier systems, including proprietary ones like Claude 3.5 Sonnet and Gemini 1.5 Pro and Flash in these human evils. It really demonstrates that you can get competitive, sometimes even superior performance without the closed data crutch.
Okay, let's break that down a bit more. Where does it really excel, and are there areas where it maybe lags?
Sure, so it does really well on questions about natural images, state-of-the-art on benchmarks like VQA, V2.0, and real-world QA. But here's where it truly stands out: counting tasks.
Ah, because of the PixMo points data.
Directly because of PixMo points and its ability to do that chain of thought, point and count reasoning we discussed. It leads all models, including the proprietary giants, on counting benchmarks like CountBench QA and their own PixMo count.
That's fascinating. So that's specific data innovation translated directly to a unique capability.
Absolutely. And it also crushes other VLMs, even the big closed ones, on clock reading. Remember that synthetic vintage watch face showing 8.26.12? Molmo nails that kind of task thanks to PixMo clocks.
Impressive. But it can't be perfect everywhere, right?
No, of course not. The paper is upfront about areas where it still lags, mostly on more advanced complex reasoning tasks, benchmarks like MMMU and MathVista.
Okay, so that points towards where future data collection might need to focus, maybe more complex reasoning examples.
Precisely. But the ablations they ran really drive home the main point. That PixMo data, especially PixMo Cap and PixMo Ask Model Anything, is absolutely critical for getting those user-preferred responses and hitting high performance overall.
And what about comparing their data approach to distillation?
This is really interesting. They found that their human-annotated PixMo Cap data performs pretty much on par with just taking the same images and using GPT-4o to generate captions, distillation.
So building from scratch was just as good as distilling from the best proprietary model, at least for captions.
Yes, which directly shows how effective their VLM-free data collection method is. And it really makes you wonder, right? It poses this important question to the whole AI community. Why keep relying on distillation if building high-quality, truly open data from the ground up works this well?
That's a powerful point.
Yeah.
And it brings us neatly to wrapping up our deep dive into Molmo and PixMo. What they've achieved here feels genuinely remarkable. A state-of-the-art VLM that is fully open. Open code, open non-distilled data, open evils, the whole package.
It's definitely more than just another model release. Molmo represents a really significant step in closing that performance gap between the big proprietary systems and open VLMs. This level of transparency, combined with the foundational knowledge they're sharing about how to build these things, it's going to accelerate scientific exploration and innovation across the entire AI community. It's a real testament to what you can do when you prioritize genuine openness and, frankly, human ingenuity in data creation.
It certainly is. So thinking forward, what does this breakthrough really mean for the future AI development? We may be looking at the start of a new era, one where open science can truly rival, maybe even eventually surpass, the proprietary giants, pushing us all towards a more democratized, more transparent AI future, something to think about.